Evening everyone, and welcome to our final live stream of the exam season. What we are going to do tonight is go through everything that could come up on your paper 2 for physics. As always, this is targeted towards OCR Gateway, but there's probably bits that overlap if you do another exam board. Post questions in the chat, I'll get to them when I can, or help each other out as we go. Hopefully we can get this done in about 1:45 tonight. We shall see how I do on that target. Right, let's make a start then. We're going to kick off with our waves topic. So the first thing we need to know is that when we talk about a wave, that quite simply is an oscillation that transfers energy. And what we find is we can divide them up into two types. We could talk about mechanical waves, which are sound and water. They need some kind of medium to travel, so they can't travel through a vacuum. And then we've got our electromagnetic waves, which do not need a medium to travel. And we're going to talk about electromagnetic waves a bit later on in this stream. In terms of the categories that we can assign to our waves, they would be called either transverse or longitudinal. Now, in our transverse waves, the vibrations will occur at right angles to the direction the wave travels. So we end up with this little diagram here. So if the wave is travelling in that direction, the vibrations are up and down because that's at 90 degrees to the direction of the travel. Now we do have our peaks or the crests and the troughs. So the peak is the highest point, the trough is the lowest point, and we will look at key features on the wave in a little bit. Our other option is our longitudinal wave, and in this case the oscillations are going to be in the same direction as the energy transfer or the direction of movement. So if the wave is going in this direction, the vibrations go in that same direction. Now we end up with two key regions here. We get these high pressure regions called compressions, and you can see that those lines are very close together there. And then we get the low pressure regions where the lines are spaced further apart from each other, called rarefactions. So what we see here is we get compressions, rarefactions, high pressure, low pressure. We've got four key terms I say we need to know as far as wave properties go. First one is the phrase amplitude. So when we're talking about the amplitude, this is going to be a symbol of A for amplitude, and it's going to be the distance from the middle. There we go. So this is our wave diagram. The distance from this midline to either a peak, or if you prefer, you could do it down to the trough. So that is the amplitude of our wave. Next one, our wavelength. This is the point from one wave to the identical point on the next. So if we use this one, so if we were measuring from peak to peak, that is a single wavelength. You could do it from any point. You could use literally this little random point here. As long as you go to the exact same point on the next wave, that is the wavelength. Frequency, quite simply, is the number of waves or the number of oscillations per second, and that's going to be measured in hertz. And then your time period is the time for one wave to pass at a given point, and because it's time, that means it's going to be in seconds. When it comes to actually representing waves in some kind of diagram form, we get two choices here. We could represent them as what we refer to as a time trace, or what we refer to as a snapshot. The key thing about these two different visual representations of our waves is that they both allow us to measure amplitude. That will always be from that middle line to the top part of the wave, or the bottom part of the wave. So to the peak or the trough, from that midline, always the amplitude. Whether it's a snapshot or a time trace, makes no difference. If we then consider our time trace, what that one is going to show us is how the displacement varies with time. Now, what we can see on this one is we can work out the actual time period. So you'll know that we are talking about a time trace because on the y-axis here we're going to have displacement, and on the x-axis will be time. So key thing is the x-axis value of time there. So what we can see is that we're getting a measure of how displacement changes with time. Now we can work out the time period because that is from any point on a wave to the identical point on the next. So if we do have a time trace, our period there, from one point on a wave to the identical point on the next. If they were to ask you to calculate the time period where they've given you just the frequency in the question, all you need to do there is 1 divided by that value for frequency, and that gives you your time period. The other option is the snapshot, and this shows us how displacement varies with distance at a given time. So what we can do on this one is measure the wavelength. Still the amplitude, as we've said, from that midline to the peak or midline to the trough. But if we take a point on one wave, go to the identical point on the next, that is the wavelength. And again, you can identify it's a snapshot because the x-axis is going to say distance in this case. Now, one thing that we do need to know about is one of the kind of bits of equipment that we can use to investigate our waves. And the thing that you probably had wheeled out in front of you for this is the ripple tank. So some of them are better than others, but generally speaking, it's a plastic tray on some legs with some kind of little vibrating bar in it. We put a bit of water in it and then we create waves. That is what a ripple tank actually is. Now, we can use our ripple tank in order to actually measure a few different things. So the first one is if we want to measure wavelength, we've got a couple of options here. So here's our little ripple tank, and if we want to measure the wavelength, quite simply, you could just drop a ruler into your tank here and then try to judge it as the waves actually pass. Clearly not a very accurate way to do this. The improvement there is to use a bit of equipment we call a stroboscope, which basically is like a strobe light, and what it does is it freezes the wave, and therefore we can measure it with a ruler far better because the waves appear to stop. Obviously they don't really stop, but they appear to, so we get a better measurement. The other option that we've got with our ripple tank is that we can measure frequency. Now, in order to measure the frequency, you can literally just put a little marker, a dot or something on the edge of the tank, and then just count how many waves pass that in 30 seconds, and then divide that by 30 to get your actual frequency. So that gives you a measure of how many waves pass a point each second. Option 2 is that you can attach a little bit of paper onto that bar, and basically as it vibrates, it's just going to hit that bit of paper. And quite simply, all you're doing there is just counting the little sounds, the vibrations that you get each second. The one that they've listed on the advanced information is a practical about the speed of sound, and this came up a few years ago. So when we're looking at an experiment that we can do to investigate the speed of sound, generally what we're looking at is something that you're going to set up with 2 people. They are going to stand a certain distance apart from each other, and you're going to measure that distance using a ruler or a tape measure, you choose. Now, do make sure you specify the equipment and that you are measuring the distance that they are from each other. What we then do is have some kind of method of making a sound, so hitting a ball on a bat, I think was the example a few years ago, shout, whatever, makes no difference, something to make a sound. And then you are going to time, using a stopwatch, how long it takes from the point of making the sound to it reaching the other person. Because we know the distance and we know the time, we can then just do speed is distance divided by time, and we've got the speed of our sound there. So remember, how are we going to do it? What are we going to use to measure things? And then how do you actually calculate the speed at the end? They're the kind of 3 key aspects of that. The other way we could do it is by using 2 microphones a known distance apart. Again, measure the distance with a ruler. And what we do is we connect those microphones to an oscilloscope. You make a sound, and then from the oscilloscope reading, you can work out how long it's taken between that sound reaching the 2 different microphones. Again, we know the distance between them. Speed is distance divided by time. This does bring us onto a calculation that I would say is highly likely to come up tomorrow on the exam paper for everyone, which is wave velocity. On the formula sheet, of course, it's just going to be your frequency times the wavelength. Only thing to look out for here is to make sure that the wavelength is in meters. If they give you a wavelength in centimeters, divide by 100 and then times that by your frequency. Do remember that when we're talking about the velocity of sound, that is going to vary when we've got different temperatures and different pressures. You don't need to know anything overly specific about it, just that it does have an influence there. Next bit is just for those of you doing GCSE physics, but it is foundation and higher, folks. We need to understand the different behaviours that our waves can take, basically. And one of the key things we're going to look at here is the idea of refraction. So what we see is, if we've got a sort of setup where a wave is travelling from one medium into another, then what we're going to see is two things could change: the speed or the direction, or both. So we are changing the velocity. Link back to our Unit 1 work there. Velocity is obviously a vector, therefore it has both a size and a direction. So a change in either the speed or the direction of that wave is a change in velocity. And this is what refraction is. As the wave moves from one medium into another, its velocity is going to change, and therefore we see this kind of bending, if you like, of the wave. You probably looked at this with little ray boxes going through plastic or glass blocks, just to show how it changes. Now, what we end up with is this kind of setup. Here's our wave coming in. This is going to be our air, so it's cold air on this side, so low velocity, and then we've got hot air on the other side. So as the wave comes in, what we're going to find is this kind of lower edge, if you like, of the wave is going to hit the hot air first. And therefore, this whole thing is going to start to bend. Now, because we're going from something that's actually cold to hot air in this case, it bends away from the normal. So your normal line just at 90 degrees to the boundary, it bends away from the normal. If it was going the other way, then it would bend towards the normal. So all we see is that this actual ray is going to bend one direction or the other based on whether it's going something more dense or less dense. One to remember here that they throw in every once in a while is that if we have a wave that hits the boundary at 0 degrees to the normal, then it will change in speed but not in direction. So if obviously the entirety of the wave hits that boundary at exactly the same time, it's not going to bend towards or away from the normal at all, it just moves at a different speed. So direction stays the same, speed however will vary. So we've got three options for what happens at this boundary then. First one, we get reflection. So if we're thinking sound, that would be an echo. Secondly, it will be transmitted, which is possible refraction at that point. Or thirdly, it will be absorbed by that material. So we've got three potential outcomes there. Still, just for the GCSE physics folks, we now need to understand ultrasound. Definition of ultrasound is any sound with a frequency of greater than 20,000 Hertz. Now, key thing to remember is obviously we as humans cannot hear these frequencies over 20,000 Hertz, so we can't hear ultrasound, but there are certain animals that can. Think bats, for example. Now, in terms of why we learn about ultrasound, it's because it's actually really quite useful to us as the human race, because it's got this short wavelength, and so we can actually focus it into this concentrated beam. If you're doing the higher tier in GCSE physics, you need to know how that works in terms of an ultrasound scan. Now, if we think about particular uses of ultrasound, then we use it to scan unborn babies, to monitor blood flow, to locate kidney stones, for example, all of those uses of our ultrasound. And the way it works is this. We've got our little ultrasound transmitter, which is also the detector, so it's a two-in-one device. What's going to happen is the ultrasound is going to be emitted by our transmitter, and what happens there is those ultrasound waves travel into, obviously, the mother's body at this point. When they hit a boundary, so basically when they hit some kind of different tissue, then some will be reflected. They will be detected by the receiver here, and it will know how long it took for that wave to travel in and back. From that, we know the speed at which they're travelling, we've known the time it's taken, so we can then work out distances. And the computer basically processes all of this information coming back from all of the different reflections and generates the image of the baby on the screen. So obviously the sort of standard NHS ultrasound is that thing you kind of squint at and try and make out images when they're going, oh look, there's its face, and you look at it and go, is it? And you do now have this far fancier kind of 4D, 3D ones that you can get that literally show you every finer detail about what the baby is going to look at before it's ever born. So gives us that little image that we can then identify any defects or problems with a baby in advance. Still just for higher tier physics folks, you also need to know that we can use our ultrasound in things like echo sounding or in sonar, so kind of aquatic uses if you like. Because what we're able to do here is look at how deep the water is. So this is a great example of fishermen looking for shoals of fish using ultrasound. When we've lost planes at sea, we can actually search for the wreckage on the sea floor using ultrasound without having to send anything down there. If we now consider what happens to sound when we just shout in an empty room, something you may well have done when you're highly frustrated with all these exams. When you shout in that empty room, the first thing you're going to hear is this slight echo. But that echo doesn't last forever. It starts to fade away, and different rooms fade quicker than others. Now, the reason that you get that echo is that initially, as that sound hits the wall, it's going to be reflected. But as it hits the wall, some of the energy is also absorbed by the particles in the wall itself. So as a result of that, our waves lost energy, and that energy has been transferred into those particles in the wall, making them vibrate and the wall a tiny bit hotter. You're not going to be able to heat your house just by shouting at a wall, but those particles have gained a bit of energy there from your wave. Obviously, if this happens time and again, eventually we transfer enough energy into the wall that the sound is not going to be reflected anymore. The next little bit we need to understand is how we hear sound, so all about our ears. So we've got this lovely little diagram of the ear that we had a look at here. So this outer bit that sticks on the side of your head is called the pinna, and we've got the auditory canal, the bit you can jab your finger in. So those two bits there are all to do with collecting the sound. Sends it down towards this little membrane here, which is our eardrum, and as the sound wave hits, it makes the eardrum vibrate. Because we've got these little tiny bones called the ossicles, or the hammer, the anvil and the stirrup resting against it, as the eardrum vibrates, those tiny bones vibrate. But they also amplify the sound. So not only are they transmitting it, but they're amplifying it. They then pass that through the oval window, which is another membrane, into the fluid-filled cochlea. Now, within the cochlea, you've also got these tiny little hairs of different lengths, and so that as the fluid is transmitting those vibrations, those hairs will also then start to vibrate. Certain hairs will vibrate with certain frequencies. That then generates this electrical impulse that travels down the auditory nerve to our brain, where we process the information, and therefore we know what we've just heard. In terms of what those tiny little hairs inside our cochlea do, the different lengths of hair that you've got correspond to the different frequencies of sound that you can hear. What we find is we've got this thing called natural frequency, which is the frequency at which the object will oscillate if it's displaced. And resonance is this large amplitude oscillation that happens when you make something oscillate at its natural frequency. So with those little hairs inside our cochlea, they've got different lengths, so they resonate at different frequencies. That means that if you've got a wide range of different length hairs inside your cochlea, you are going to have them resonating at a whole range of different frequencies. You will hear a wider range of sounds. As you get older, then you start to lose the shorter hairs. So those shorter hairs correspond to higher frequencies. This is why you'll find that some shopping centres or sort of town centres have this thing called the mosquito sound, which just plays this high frequency sound that basically gets teenagers like you guys to disperse, while all the old folks like me can just carry on about our days without having a clue there's even a sound playing. Because you've got those shorter hairs, so you hear this sound that's quite uncomfortable. People that are older, they've lost those shorter hairs, they hear nothing, and therefore no impact. Right, back for everyone, so combined triple, higher and foundation folks, we're going to have a look at electromagnetic waves. The first thing to make sure you know is the good old electromagnetic spectrum. There's a great song that I've played to my lot that I'm sure is stuck in their heads to this day that you can use, or you can just memorise them. But you do need to know the correct sequence of these electromagnetic waves, because sometimes they give you a little gap fill exercise, missing out a few of these, fill in the right ones, easy marks in theory. So, radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. Do notice that we have this very clear pattern. If we've got a long wavelength, we've got a low frequency. Whereas if we've got a short wavelength, we have a high frequency. So just remember that little pattern there, that the longer the wavelength, the lower the frequency. And then you can apply it to any given scenario. Now, we refer to these as electromagnetic waves because they are literally electric and magnetic. So they've got these two different fields that are oscillating at 90 degrees the direction of the wave. So you've got your electric and then you've got your magnetic. So electromagnetic waves. All electromagnetic waves will travel through a vacuum at a speed of 3 times 10 to the 8 meters per second. So 3.0 times 10 to the power 8 meters per second, that is any electromagnetic wave. So if they ask you how quickly ultraviolet travels, if they ask you how quickly microwaves travel, 3 times 10 to the minus 8 is the answer, 3 times 10 to the power 8, sorry, not minus 8, is what you need to actually write down there. Another phrase we should know here is the word source. If we're talking about a source, that is something that is emitting electromagnetic waves. Other objects will then absorb those electromagnetic waves that have been emitted. Think about your skin absorbing something like infrared. The electromagnetic wave itself is purely transferring the energy from the sources to those absorbers. If you're doing higher tier, combined or GCSE physics, this bit's just for you. What we need to understand is basically how radio waves are able to transmit a signal from one place to another. What we have then, our radio wave, remember, is an electromagnetic wave. So that means it's got this oscillation of both electrical and magnetic fields. So what we end up with is, in our little transmitter, what we're going to have is this oscillating potential difference. So that means we're going to get electrons moving backwards and forwards with that oscillation across the wire. As a result of that, we're going to then produce this changing electric and magnetic field, the electromagnetic wave, the radio wave. So that is emitted from our transmitter. As it travels, eventually it's going to come into contact with some kind of piece of metal, usually your receiver. And when it meets that piece of metal, the electrons in the metal structure itself are going to start to move, and therefore we generate this electric signal. So the whole idea here is that we've got this oscillating potential difference in a wire, creating our electromagnetic wave, the radio wave, and then when that meets a metal, it then makes the electrons in the metal move to produce the electrical signal that is then obviously interpreted by your radio or TV, etc., to give you that final signal that we transmitted. For everyone, we need to know about uses and dangers of electromagnetic radiation. So in terms of our uses, there's loads. Microwaves in things like your mobile phones, your satellites, etc. You've got radio waves, radio and TV as the name suggests. Your remote controls use infrared. We're going to use visible light for various communication. Think the oldie ship communication with little flashing lights, etc. But we can also use infrared and microwaves in cooking food. So if we think microwaves first of all, they use microwaves. It's not a misleading name for once in science. So the microwave oven emits the microwaves, and they're then absorbed by fat and water in the food. What we see here though is that those microwaves are able to penetrate a few centimetres into the food. So they'll be absorbed by particles a few centimetres into the food itself. Then that energy, to cook right through to the middle, has to be transferred by your typical conduction. If we compare that to our kind of traditional conventional ovens, the ones that use infrared, that's only absorbed by particles on the very outermost surface. So that means we're going to have to transfer that energy by conduction a lot further, because we're not absorbing as many sort of particles directly with that electromagnetic radiation. So infrared only absorbed on that surface, and then it has to transfer by conduction right the way through. Hence, much slower at cooking your food than the microwave, because they penetrate a few centimetres in. So it's done a lot of it already before the conduction has to kick in. If we think about something you're probably very familiar with, all your different kind of CDs, DVDs, Blu-ray, game discs, whatever they may be, any kind of disc format, they are using visible light in the form of a laser to be read. If we think ultraviolet, best example here is probably your skin. It's great at using ultraviolet radiation from the sun to make vitamin D, and that means that you don't get a condition called rickets, and that's basically where your bones kind of bow, really. You can also use ultraviolet in forensics, so identifying forged banknotes or looking for blood and bodily fluids and all that kind of fun. And we can use X-rays to kill cancerous cells and obviously produce images of broken bones or potentially broken bones. And finally, our gamma rays will kill bacteria and kill cancerous cells as well. So those are our uses. In terms of the dangers or the risks of these types of electromagnetic radiation, then firstly, we will find that ultraviolet, for example, has the link to skin cancer. The reason for that is that ultraviolet being absorbed by the skin cells are actually going to damage the DNA. If you damage the DNA, you're more likely to go on to get cancer, and obviously skin cancer if it's in your skin. If we're talking about your eyes, then exposure to too much ultraviolet can lead to development of cataracts. If we think about X-rays, one of their key problems is they can damage those cells and cause cancer, hence why the radiographers, the people that take the X-rays in the hospital, actually stand behind that LED screen, or they go into a sort of attached room when they're actually doing the X-ray itself. Gamma rays, obviously the big risk here is that they can also kill perfectly healthy cells, or they can damage the cells in the body as well. So even though things like X-rays and gamma rays have a use in terms of medical treatment, there's also a risk to them as well. For those of you doing GCSE Physics Higher Tier, we need to know about how we can use electromagnetic waves for imaging purposes. The simplest kind of image really to talk about is a thermal imaging camera. So these produce this thing called a thermogram, which basically just gives us different colours to show us the different temperatures of objects. And the way that this happens is, inside this thing called a charged coupled device, or a CCD, there are these pixels that absorb infrared radiation. Hotter objects emit more infrared radiation, so that means that they would absorb a greater amount, and as a result of that, we produce an image. Generally, those colours are then added by a computer, because that just makes it a little bit easier for us to interpret. If you know that something that is bright red is very hot, whereas something that blue is cold, it just makes it far easier to work that out. In terms of how X-rays work, then what we find is we've got obviously bones and soft tissue around them. So the skin, the muscles, that's soft tissue. Bones absorb X-rays. The soft tissue does not absorb X-rays. So what we find is when they place that little photographic film underneath your potentially broken arm, and then they're going to shoot the X-rays down from above basically, where the bone is, they will be absorbed, and therefore you won't have any reaching photographic film, whereas the soft tissue, it will pass right through and therefore absorb the X-rays. Now, where the photographic film absorbs X-rays, it becomes darker, hence why the bones appear white, the rest of it's kind of this greyish black colour. We can also use this thing called a CT scan, which is allowing us to look inside the body, again, without the need for cutting you open, which is always useful. We can also use gamma rays in something called a tracer in medicine, and a tracer, quite simply, is some kind of object that's going to emit this gamma radiation that you are going to inject, swallow or inhale, depending on what we're looking at, and then we detect those gamma rays using a gamma ray detector, basically. On the computer screen, you then get these images so we can identify blockages, leaks, etc., without, again, having to cut people open. It's the same idea in terms of underground pipes. We can use, obviously, gamma radiation as a tracer there, and then you just run, basically, a detector across the surface, and then what we'll find is you get this greater concentration and then a sudden drop-off where there's a leak. So that means we will only dig up that little patch of the road rather than the entire pipeline. For all of you doing GCSE physics, the foundation and the higher tier, we need to know about ray diagrams here. Now, in terms of ray diagrams, this is something you should have done back in Key Stage 3, and there's a few key points to remember. Number 1, use a ruler. Don't try freehanding this. Number 2, we are obviously going to represent our rays with a straight line drawn with a ruler and a pencil. You are then going to make sure that you add arrows to show the direction it moves in. Quite frequently on these ray diagrams, one of the marks is for the direction, so the arrowheads. So don't forget the arrows. Don't just draw lines with no arrowheads, always add the arrows. So, 2 kind of key diagrams to start us off. Simple reflection. We have a mirror. We've got our ray coming in here, and then between the normal and that ray is the angle of incidence. We also have the angle of reflection. Hopefully we know the law. Angle of incidence must be the same as the angle of reflection, and there is our second one. Now, they never specify you need a protractor in the exam, so just do it by eye, but go careful. Don't just rush it, because we're looking for it to be approximately equal. So if you've drawn a line that's somewhere down here, clearly not getting a mark, but if it's just kind of a little bit off, you're probably still getting a mark there. Then add your 2 arrows onto there. Please make sure that your points actually do meet, and they meet at the surface of the mirror. They're not just randomly floating in the middle there. Option 2, this is our refraction. So we've got our ray coming in here, air, glass block for example. There's our normal line. Because we're going from less dense into more dense, we bend towards the normal. On the other side, if we were adding here, it would bend away from the normal because it's going from more dense into a less dense medium. Again, add those arrows just to show the direction of travel. One thing that we should remember is we live on a planet that is basically a giant sphere. Therefore, we've got this curvature to the surface. The Earth is not flat, it is curved. Now, what that means is that when we actually want to transmit some of these waves over long distances, we hit a problem because waves travel in straight lines. So if we're trying to transmit over a very large distance, the curvature of the Earth would prevent it. Instead, we've worked out that we can actually send radio waves basically up into one of those layers of the atmosphere called the ionosphere, and that will reflect them back down. So what we use is basically part of the atmosphere to reflect the radio waves back down, and then it travels a much greater distance, overcoming the problem of the curvature there. If we wanted to send something obviously beyond the ionosphere, then we'd use things like high frequency radio waves or microwaves in order to get them through that up to the satellites that are orbiting around the Earth. And we'll discuss satellites in our P8 topic at the end of tonight's live stream. Just for those of you doing higher tier physics, you need to know about sort of transmission and absorption of our electromagnetic waves. So what we actually find then is that the wavelength is going to determine what happens to these EM waves. So if we think about your kind of wall, first of all, that's able to transmit radio waves. So your radio waves are going to be able to travel through a wall, hence why we can get radio reception in a house. But something like visible light is not transmitted through a wall. You can't see through it. So they're absorbed. If we think about our atmosphere, that is very important for life on Earth because it's going to absorb X-rays and gamma rays, which otherwise would basically kill all life on Earth. So the atmosphere absorbing those X-rays and gamma rays protects us from those two problematic rays. Now we come on to the lenses part of the waves topic. So when we're talking about lenses, we're going to look at two types. We're going to start off by looking at the convex or converging lenses. Now these are the ones that are, to all intents and purposes, going to bend the rays of light inwards. So this is the kind of diagram you see with your convex lens. Now your convex lens is quite obvious because it's the one that kind of has a fatter middle. So what we see, here's our rays coming in, and then you can see they're all just travelling in parallel initially. What happens is, when we actually get to this central point of the lens, they're going to start to refract and they're bent inwards. Now what we do is you can actually see that these lines all meet at this key point here called the principal focus. If we measure the distance from our centre of the lens here to the principal focus, that's what we refer to as the focal length. The other option that we've got is the concave or diverging lens, and this is the one that basically spreads the light outwards. So here it is. You can always spot it because it bends in like a cave, hence concave. There's our little cave. So again, we've got our light coming in to the centre of our lens again, but then when it gets to that point, those rays are all going to bend outwards. Now what we find is, if you've got this diagram and they want you to sort of show where the virtual focus is, all you've got to do is just extend each of these lines back on themselves, and there will be a point where they all meet. That is our virtual focus. And the focal length in this case is from the centre of the lens to the virtual focus. The reason that these lenses are quite important is because they allow us to correct vision defects. Short sight, long sight, both use lenses in order to correct them. So if you are short-sighted, that means that the objects in the distance are going to be blurry. Then what we're seeing there is basically the rays are trying to focus in front of the retina. So they're not focusing on the back of your eye, the retina, they're focusing a little bit too far forward. So what we use there is a concave lens, because that one spreads it out, and therefore it initially spreads out those rays of light before they enter your eye, and then as it goes through the lens, it will actually focus it perfectly on your retina. If we're talking long sight, that means your near objects are blurry, and what we're going to use this time is a convex lens. So basically that one just starts to refract them inwards before they pass through your lens in that case. Both end up correcting your vision so you get nice clear sight in theory. If they're mean, they could ask you to draw a ray diagram with the lenses. So this is what they're really aiming for when they give you that kind of question. So the first thing that you are going to do is not going to have all of this, obviously. Some of these lines are going to be missing. The first thing you're going to do is you will draw a nice little horizontal line from the top of the object to the centre of the lens, and that runs parallel to this principal axis. That will be plotted on the actual diagram they give you. So a line goes parallel from the top of your object to the centre of your lens. What we then do is we draw a ray that goes from the lens through the focal point, and again that will be marked on the diagram for you. Finally, what we're going to do is draw a ray from the top of the object through the centre of the lens. So you can see this one here goes straight through the centre. Where those two lines meet is going to be the top of your image. So that just gives you your point that they're both meeting, and therefore the top of your image there. Don't forget to add the arrows as always, because we are talking a ray diagram here. For GCSE physics folks, you might also need to know the uses of some lenses. So in terms of our convex lenses, magnifying glass, camera, projector, all use a convex lens. For concave lenses, we've got things like your spy holes. Now, where the convex lens is concerned, the type of image differs depending on the use that we've given. So in a magnifying glass, it's a virtual image that we get. It's magnified, name is the hint there, magnifying glass magnifies the image, and it's upright. It's the same way around that you look at it. If we think about a camera, it's a real image that's diminished, so it's smaller than the actual thing, and it's inverted, so it's upside down basically. With our projector, so projectors on the ceiling of your classrooms, they're real images, magnified again, and inverted. So, when it comes to our concave, what we find is they are going to be virtual, diminished, and upright. Hence why when you look through a spy hole, you can see a person, but they appear a little bit smaller, but they're still upright. For those of you doing higher tier physics, you need to know about the light and colour just to finish off this first unit. What we find is if we pass white light through a prism, then it's going to split that white light into those individual colours of the visible spectrum. So red, orange, yellow, green, blue, indigo, violet. The reason that happens is because of a process called dispersion. Now, the reason that they're all going to split out from each other through this process of dispersion is that each of those colours actually is a different frequency. So each frequency of light travels at a different speed in glass, and therefore they're going to be refracted a different amount. And the higher the frequency, the greater the amount of refraction. So all we see there is because they're all different frequencies, they all refract to a slightly different degree, and therefore they split out into the individual colours that we can see. If we're talking filters, then basically a filter is something that is going to absorb all frequencies of light except for the one that matches itself. So if we have a red filter, that will absorb all frequencies of light except red. If you put a second filter in, so you had a red and then a blue, what we would actually find is that you would have, in the red filter, everything absorbed except the red, that would pass through, but then when that hit the blue filter, that red light would be absorbed, and therefore anything on the other side just appears black. So don't forget, two different colour filters absorb all frequencies of light, so they look black. Anything else, if it's a single filter, absorb all frequencies except for the one that's the same as your filter, and therefore it looks whatever colour that is. Right, that's our waves topic. Next up is the radiation topic. So this is P4 or P6, depending on if you're combined or triple. First thing is for everyone, so combined, triple, foundations and higher folks. We get our lovely overlap with our chemistry again. We need to know about atoms. So first thing is that the nucleus of an atom is made up of the protons and the neutrons. Remember, electrons are in shells. You should hopefully know that little table that gives you the relative masses and the relative charges of protons, neutrons and electrons. And because our nucleus is made of protons and neutrons, protons is positive, neutrons no charge, therefore the nucleus will always be positive because of that. We then have an overlap with kind of three key terms from our chemistry here. So isotopes are atoms with the same atomic number but a different mass number, or we could phrase it as the same number of protons and electrons but a different number of neutrons. We need to know that the atomic number is the number of protons, which is always the same as the number of electrons. So if you've got 6 protons, you have 6 electrons in an atom. And the mass number is your number of protons plus the number of neutrons. So if you want to work out how many neutrons there are, mass number minus the atomic number. The reason that we go through that little bit at the start is we're going to have a look to see what happens to atoms when they undergo this process of radioactive decay. Most atoms are stable, so they don't decay. If you've got an atom with an unstable nucleus, then it will emit radiation as it undergoes this decay process. So what we find, there are 4 types of radiation you need to know. Alpha, beta, gamma and neutron. So alpha, this is going to be an alpha particle, which we actually show as basically the symbol for helium, He, and then we would have its mass number of 4, atomic number of 2. So that would be our equation symbol. Beta particles, these are fast-moving electrons, so the little symbol for electron is lowercase e, 0, -1. Gamma, that is purely an electromagnetic wave, so it has no equation symbol because it is energy, that is it. And then our neutron, that has the little lowercase n as its symbol, 1 and then 0. It's worth remembering at this point that neutrons can actually undergo decay to make a proton and an electron. In terms of how we work out whether something is emitting radiation or how much radiation is present, we use a bit of equipment called a Geiger Muller tube or a Geiger counter. Now, what you'll hear on that are these tiny little clicks, so it just sounds like clicking. And those little clicks are tiny currents produced as the radiation is ionising atoms of gas inside the tube itself. So what we actually find is this links into one of the really common questions about radiation, which revolves around this principle: the different penetrating abilities of alpha, beta and gamma. So our alpha particle is stopped by a few sheets of paper. Beta particles stopped by a few millimetres of aluminium, but they generally pass through paper. And then your gamma rays through the paper, through the few millimetres of aluminium, but they will only be stopped by few centimetres of lead or metres of concrete. And even then, some can still potentially get through. So gamma is the most penetrating, passes through the most things. Alpha, the least penetrating. They can give you a question where they give you a little table of different activities based on what it's passed through and ask you to identify the type of radiation present. So if you see something that starts off with a certain activity and then it drops down very low after going through some paper, it was alpha. If you've got something that stays the same after the paper but only drops down once it's gone through the aluminium, it would be beta. Sometimes they will put a combination of them in there, so just watch out for that. If you get a drop after one and then a later drop after the other, it could be both alpha and beta being emitted. So just watch out for the tricky little moment there. What we find then is we refer to these types of radiation as ionising radiation. And by that we mean they have the ability to remove electrons from atoms to produce ions, hence ionising. In terms of the ionising power, what we find is the opposite to the penetrating power. So alpha is the most ionising, beta in the middle still, and gamma the least ionising. So realistically, if you know one of those and the sequence it goes in, you reverse it for the other. What we now need to know are the different decay equations. Now, these are usually very generously marked, so you can sometimes bag a nice 6 marks just on these 3 decay equations. And to be honest, they are so easy you should all get all marks on them, because all we're doing is adding or subtracting. That's pretty much it. If you remember the simple rule that your mass number and your atomic number on the left must be the same as the total mass number and atomic numbers on the right, you've got it. So they will generally give you something on the left, so what you start with, and then you're going to have the 2 things being made on the right, and some of the numbers are going to be missing. All you need to do is, if it's something on the right missing, if you've got, say, 240 as the mass on the left, and they've given you 236 of the other one, missing one, just 4. The difference. So quite simply, you can see you are purely adding up to make sure totals on the right are the same as the left there. So in alpha decay, we are clearly losing an alpha particle, which is that helium nucleus. So it will have a mass number of 4 and 2 as the atomic number. So quite simply, the other substance will be a mass number 4 less than it started as, and your atomic number 2 less than it started as. Beta decay, this one is where we're going to see a neutron decaying into a proton and electron. So what we see in our beta decay then is that we are going to see the mass number remaining the same, because our neutron, remember, is going to change into a proton. So they're both in the mass. If we lose one, we gain one, just cancels out. So mass doesn't change, and we then find that we have to add basically 1 onto the atomic number. So we're adding 1 onto the atomic number because we've gained the protons, which is the number of protons. We then need to add our symbol for our beta particle, which is the electron, so lowercase e, 0 at top, -1 underneath. Gamma won't be a decay equation because there is nothing to say. It is literally emitting energy. So gamma have no mass, no charge. They are purely electromagnetic waves. So no change to mass, no change to atomic number. In our neutron decay then, what we find here is that you would start off with something with a mass number, say 5, atomic number of 2. We're then obviously just going to have it go mass number down by 1, atomic number stays the same. Because remember, the symbol for our neutron is our little lowercase n, 1 for the mass, 0 for your atomic number. So all we're doing is making sure those numbers add up to the same as on the left as they do to the right. Still, for everyone, we need to know about this idea of half-life. So when we talk half-life, basically what we're looking at is how long it takes for the activity of this radioactive material to reduce by half. So we could phrase that in a different way of saying it's the time it takes for half of the unstable nuclei to decay. We do this by a measure of their activity, and activity is measured in these units called becquerels, and we use a Geiger counter to get that activity. Now, there are 2 ways that we could see this. The first one would be a little graph of our half-life. So you generally get a graph something like this. Now, what we will have is our initial activity at the top there. So whatever that little bit there is, whatever the number on there, that's the initial activity. That's where we start. So after a single half-life has passed, if that was 100, then we would be down at 50. So quite simply, you literally halve it. So if we wanted to know how long a single half-life was, start 100, work out what half it is, 50, and then we just draw a little line across the curve, bring it down, whatever the time at the bottom here is, that is the half-life. So we can do it from a graph. Alternatively, we can do it through calculation. So they would give you something telling you how many days it's going to exist for, they will tell you how long a single half-life is, and they will give you the initial activity. They'll then ask you to calculate the activity after a certain time frame. First thing, work out how many half-lives have passed, so total time divided by the time for a single half-life, and then obviously, depending on how good you are with fractions, you could work out the fraction it would be, or if you're not great with fractions, type the initial activity into your calculator and then divide by 2 however many half-lives it was. You get your answer either way. For everyone, we also need to know about the arrangement of our electrons within the atom. So we start off with this same idea we looked at in chemistry, that electrons are arranged in these shells. Now, those shells are at certain energy levels around the nucleus. Different atoms will have different energy levels, as we kind of established in chemistry. Now, what we find is that the electrons will usually occupy the lowest possible energy level, the one closest to the nucleus. However, if they absorb some kind of electromagnetic radiation, what we can see is those electrons can become excited. So that basically means they've absorbed an amount of energy and therefore they move to a higher energy level. So at that point we have excited electrons in an energy level above where they should be, and what then happens is they're going to drop back down, eventually emitting that energy as well. So when they absorb energy, they jump to a higher energy level. When they then drop back down, they must release that energy. This brings us on to the idea of these absorption and emission spectra. If we're talking about an absorption spectra, first of all, then what we find is if you pass light of all frequencies through a gas, some frequencies are absorbed. And the absorption spectrum shows us which ones they are. You get these little black lines. And that's just based on what those atoms actually absorbed, so what actual energy levels were changed. If we then look at the flip side, the emission spectra, this is basically what it's going to release as those electrons drop back to their original energy levels. So you will then get different frequencies being emitted based on how far they have dropped. One thing that they do like to ask every once in a while is about background radiation. So when we're talking background radiation, this is just looking at sources of radiation you're exposed to all the time. Vast majority is radon gas. You can then get things like your medical uses, you've got ground, you've got cosmic rays, food and drink, all of those are background radiation. Two key terms you should know here. Contamination, this occurs when our radioactive material is taken inside the body or is on your actual skin. And irradiation is when the radioactive material is outside your body. So don't mix up those two terms, they're not interchangeable. Contamination is taken into your body or on your skin, whereas irradiation is something radioactive outside your body. Do remember the key problem with all this radiation is if it enters our body, the DNA can become damaged and that can lead to cancer. In terms of another use of our radiation as far as medicine goes, then for those of you doing GCSE physics, you need to know about the gamma knife. When we talk about a gamma knife, this is basically the device we're going to use to kill cancerous cells. It's a source of gamma radiation that we can move around the body, but it's always focused on the tumour cells. So it will give the tumour cells a high dose of radiation, enough to kill them, but the healthy cells around it won't get that high dose and therefore should be okay. We then come on to the idea of nuclear fission, first of all, and nuclear fission is the splitting of a large nucleus into two smaller nuclei and neutrons. Now, what we find is that if the nucleus of an atom absorbs a neutron, then fission becomes more likely. And what we see in this process is if you fire a neutron at the nucleus of an atom and it becomes absorbed, then it's going to split to produce these two smaller nuclei and it will release 2 or 3 neutrons at the same time. Those ones will then be able to go on, they will be able to join with other nuclei and leads to this then continuing. Two good examples to remember, uranium and plutonium. Both of these are fissionable substances. That means we can split them easily. That's what we put in our power stations. So nuclear power stations use this idea of nuclear fission to heat the water. That means the water becomes steam, steam drives the turbines, turbines turn the generators, generators make the electricity. And what we find is the reason that nuclear power is quite interesting is because it will generate a much greater amount of energy per kilogram of fuel compared to the combustion reactions in our fossil fuel power stations. However, there is a certain risk to these in the fact that every fission reaction releases 2 or 3 neutrons. Those neutrons can then obviously be absorbed by other nuclei, causing them to split, and if we don't have some kind of control mechanism, we just keep getting a larger and larger and larger reaction each time. Because remember, every nuclei that splits is potentially releasing 3 neutrons that will cause another 3 reactions. So we get this idea of a chain reaction. Now, the key thing here is if we're talking about our nuclear power station, you don't want an uncontrolled chain reaction. That's called a meltdown. That's bad. So what we use are these things called control rods, which just absorb the additional neutrons. So quite simply, if the reaction is getting a bit too much, we lower those control rods in, they absorb the additional neutrons and bring it under control once more. If you go with a nuclear bomb, no control rods, therefore the fission reaction just keeps growing and generates this massive amount of energy very quickly. The second kind of nuclear reaction we need to know is nuclear fusion. Now, fusion is where we're going to join 2 lighter nuclei together. So 2 small nuclei fuse or join together in nuclear fusion. And this is what's happening in things like our sun, for example. So those little hydrogen nuclei fuse together, they form larger nuclei, they then fuse together, and so on. Now, we've not managed to harness this as a way to generate energy here on Earth, because the actual repulsive forces, so the forces pushing away of the protons, because they're both positive, are pretty tricky to overcome here on Earth. It can occur in the sun because we've got really high temperatures and high pressures. So the pressures keep them close and the high temperatures move them quick enough to cause that fusion. So we can do it in a star, we can't do it here on Earth yet. Next up is our energy topic then, and this has a whole ton of calculations in it. This is pretty much where you're going to just get your formula sheet and then work out which calculation goes with which question. We're not going to go through all of the different examples here. We do need to know the different types of stores that we have for energy: chemical, thermal, kinetic, gravitational, elastic, nuclear, electrostatic, and magnetic. So make sure you know those different energy stores. There are associated calculations on your formula sheet for each one. All you need to do is look at the question and work out which one you need to use. When it comes to transferring energy from one place to another, then we are going to use either mechanical means, electrical means, heating by particles, or heating by radiation. And again, if we're talking about a mechanical transfer, on your formula sheet, you will find work done, force times distance. Use that. If we're talking electrical transfer, that's going to be power times time. Again, on your formula sheet there. Worth remembering the law of conservation of energy. Energy cannot be created or destroyed. It will only be transferred between those different stores. So what we can actually do with that understanding is carry out these things called energy analysis diagrams. So they're these little box things. So what we have is energy in our initial stores, and then we see the energy in our final stores. The kind of key thing to remember about these is however much energy we have at the beginning must be the same as the total energy we end with in the different stores. All we're doing is transferring, in this case, from the chemical store to the kinetic. So whatever we've lost from the chemical has been gained by the kinetic. We can't just lose energy or make more energy there. Now, you will have calculations associated with this, but as I say, just read the question, work out which one you need to use there. We will find there is going to be something on power on this actual thing because it's listed on our advanced information, power and efficiency. So on all our electrical devices, we have a power rating in either watts or kilowatts. When we talk about power, this is the rate of transfer of energy. And they've asked that as a one marker before, what is the definition of power? So the rate of transfer of energy. The higher the power rating on your device, the greater the amount of energy transferred per second, so the more fuel it needs to run. So basically we would be in a much better place if we all used low power devices in theory. They can tie this into a question that then goes on to talk about the cost of running an appliance. Now, there's a range of ways that they could do this, but again, you've got your formula sheets, so just look at it and see what you've got, okay? So you might need to calculate the work done first of all, which is power times time. You might need to calculate the power before that, work done divided by time. There's a range of different ways they could phrase this for you. If you then want to work out the cost, once you know the work done, just times it by your cost per unit. They will tell you that in the question itself. One of the things that ties in to this whole idea of energy transfers is the efficiency at which they occur. Now, when we talk about any electrical appliance, we've got energy flowing through some kind of a wire. So we've got a current flowing through a wire. When that happens, the wire heats up. Now, that means rather than the energy going to our intended store, we are transferring some to a thermal store. So we are wasting a proportion of energy. So again, they could ask you about energy efficiency calculations here. We could be looking at our specific heat capacity questions. All of those again on your formula sheet. So just use the relevant ones to work out your differences. Now, in terms of another way that they can set out this whole idea of efficiency, is they could ask you to draw or interpret this thing called a Sankey diagram. Now, quite simply, the width of the actual bars here is representative of the amount of energy. So if they ask you to draw one, then the width of these is going to be important. You've got to stick to a scale. So in this example, we've got 36,000 here, and each of these is 18,000, so this has to be half the width of that one. and that one obviously is the other half. Now, usually they give you a bit of graph paper to do this to make it a bit easier, and just label it up afterwards. One of the key things here when we think about sort of efficiency is the idea of dissipation. Now, if we're talking about dissipation, this is where we're transferring energy to stores that aren't useful. So they're ones that we can't use for that kind of working or heating purpose of our appliance. They're going to something completely useless to us. So this could be, if we think about vehicles, for example, then the useful bit is making the vehicle move. But we get friction between the different bits of the engine that then leads to it being transferred to the thermal store of those bits of engine. So that is going to be dissipated. And do remember, the ultimate ending up place of all of this energy is the thermal store of the surroundings there. If we want to minimise our energy losses through dissipation, we can lubricate things or we can insulate them. Look at the scenario they give you. If they're talking about something moving, lubricating is the answer. If they're talking about something creating heat that is lost, then we're talking about insulating. So just apply the right principle to that scenario. Now, one of the things that they can link into here is good old insulation. So hopefully we know that our homes have some form of insulation, I hope. And basically that means that when we use our heating, it's not all just being transferred straight out into the surroundings outside. It's hopefully staying within our buildings, making us a bit warmer. We will find that the better insulated your house, then the less energy you will transfer from the inside to the outside. So what we're really looking at is an idea of thermal conductivity. So thermal conductivity just tells you the rate at which it transfers energy. So something with a high thermal conductivity is going to then transfer energy out much quicker, therefore you see a more rapid drop in temperature. They can throw in questions here to do with like practicals to do with insulation. So if they ask you how you could obviously change the actual insulation, add more layers to it. You know, how do you measure the temperature? Use a thermometer kind of thing. So use the same volume of water. Think about variables you need to control there. So volume, starting temperatures, whether it's got lids, etc. Now, the last little bit to think about here is if you're doing higher tier, just ways that we can improve efficiency. Now, to improve our efficiency, we've got to reduce the wasted energy in some way. And the actual method that we do for that is going to vary depending on what the scenario is. So if it's something where we are losing that energy as a result of kind of a heat transfer, then we'd insulate it. If we are looking at something like light bulbs, it might be that we're swapping over to LEDs rather than the old halogen bulbs, because they use a much lower power than the old bulbs did. So again, they're using fuels more slowly and therefore making them more efficient. Right, on to our final topic then. So P6 for those who are doing combined, P8 for the triple folks. And the first bit here is all about motion. This one usually has the really blatantly obvious questions that can simply say, suggest a bit of equipment that you would use to measure distance, or suggest a bit of equipment to measure time. So we're literally looking for rulers or tape measures to measure distance and a stopwatch to measure time. It really is that obvious. Don't overthink it, even if you're doing a higher tier paper. Sometimes there are simple questions there. Don't forget we do have a couple of calculations that will come here. We've got speed and we've got acceleration. Both on your formula sheet. Just remember to use it with a calculator throughout your exam. Two terms it's worth remembering here: precise and accurate. If we talk about something being precise, that means that the data's got a small range when it's repeated. Whereas if we are talking about accurate data, that means that the values we've obtained are close to the true value, so the actual value we should obtain. So two terms that we shouldn't use interchangeably there. Now, the next little bit is basically the how to avoid crashing your car part of the topic. So we start off with the idea of reaction times and thinking distances. So your reaction time is the time it takes from seeing something to having a reaction of some description. And typical human reaction time is about 0.2 seconds. We can do an experiment to measure your reaction time, which you may well have done, where you basically drop a ruler and try and catch it. Depending on where you catch it, will then convert into a reaction time. You might also have used a computer reaction timer, way more accurate than dropping a ruler, because we don't need to make sure the ruler is vertical, you don't need to make sure that it's exactly the same height above the hand, that your hand and your thumb and finger are exactly the same distance apart, etc. Literally a computer, you click the mouse when you see something change. So far more accurate and avoids that error that we get from humans. Now, when it comes to our cars, we need to understand 3 distances: thinking distance, braking distance, and stopping distance. The first one is the thinking distance, and this is the distance travelled in the time it takes from seeing a potential problem to actually getting your foot onto that brake pedal. So don't forget, because it is a thinking distance, make sure that if you're asked to define it, you have the word distance there. In terms of what would lead to an increase in thinking distance, this is something that's going to affect the person. So drinking alcohol, using drugs, being tired, distractions, increased speed. Word of warning, they do like these questions, and usually it's a couple of marks, but it's easy to lose the marks. First of all, make sure that you read the question, because quite often they will say, increased speed is one reason that thinking distance increases, suggest 2 other reasons. You can't obviously put increased speed because it's in the question itself. You don't get a mark for just writing the same thing from the question again. Second one, go careful not to include 2 things that are going to be the same marking point. So alcohol and drugs tend to be marked as the same point because alcohol technically is a drug. So I would suggest that you remember alcohol, distractions, and increased speed, because that way you've got 3 potential answers depending on what's in the question. You will only ever be asked to give 2. The second one, our braking distance. This is the distance travelled in the time it takes from putting your foot on the brake to coming to a complete stop. So what we find here is that the factors that are going to affect your braking distance are ones that are more to do with the actual car itself. And the phrasing here is important. If the question asks you to name 2 factors that would increase the braking distance, you need to be quite specific in your phrasing. So you would have to say icy roads, wet roads, poor or bad conditions of the brakes, poor tyre condition. You can't just say brake condition and the weather, because that's not specific enough. A beautiful, dry, sunny day is not going to increase your braking distance, whereas an icy or wet day will. So go careful on that one, and again, watch out for increased speed being in a question. Don't just write it down again. We then come on to our third one, the stopping distance, which quite simply is your thinking distance plus the braking distance. So just remember that thinking distance, that's things that affect the human. Braking distance, things that affect the car. Stopping distance is thinking plus braking distance added together. And when you learn to drive, you will see this a lot in things like your highway code, your lovely little graph that shows you how it changes with different speeds. So what we'll notice is that as far as the thinking distance goes, there's a very clear pattern there. So this one's going up in 20 miles an hour, I think it is. And that 20 miles an hour equates to a 6 metre increase in your thinking distance. So however many 20 miles an hour you add on, always 6 metres of thinking distance each time. In terms of the braking distance, that one is not in that same little pattern. You can see it actually gets larger the further up you go. And that's all down to the fact that it's not just going to be this linear pattern. So don't forget that as far as we're going, thinking distance is linear. You can see it in a little graph down here. So thinking distance is a linear increase, whereas your braking distance is not, therefore stopping distance is not. Now, the next little bit is basically looking at what happens if you fail to drive safely and therefore have crashed your car. This is basically how to avoid death when crashing cars section. So what we need to understand is that when you crash, basically your car is coming to a sudden stop. We're seeing a very rapid change in your velocity. So because we see a rapid change in velocity, that's going to influence the force experienced by the people in the vehicle, for example. The greater that change in a shorter space of time, then the greater the forces that act on us. We've got certain features built into cars to try to avoid the severity of the injuries that you would sustain. First one is your seat belt, something you should wear every time you get into a car, of course. So your seat belt quite simply has a small number of elastic fibres in there, so that when you actually crash, the seat belt is going to allow you to move forward a small amount, and then it stretches ever so slightly to bring you to that slightly slower stop. Now, the longer it takes you to come to that stop, the safer it is, because what we actually find is it reduces the forces acting on you. If you didn't wear a seatbelt and were in that same crash, then you literally keep moving forwards at whatever the speed you were going at in the car until something else stops you. Usually dashboards, seats in front of you, windscreen, things you don't really want to collide with at high speeds. That's not to say that seatbelts are 100% safe. You are guaranteed just to walk away without a single injury. You are likely to get bruising across your ribs and chest, etc. You could, depending on the speed that we're travelling at and therefore the size of that negative acceleration, suffer from compression injuries as well. So this is why we also have speed limits on our roads, because even in a case of a crash, you should be relatively safe if you're wearing the correct safety equipment. It all comes down to that calculation, force is mass times acceleration on your formula sheet. So for those of you doing higher tier, you will also need to know about some of the other ways that we can reduce forces. And we've got crumple zones in our cars. So modern cars these days, generally if they're in a crash, they're written off. And that's because they're pretty much designed to collapse in a specific way. So that's a crumple zone. There's different densities of metal that mean it pretty much folds up safely. We also have airbags, again the idea being they're going to give you that little bit longer to come to a stop safely, therefore reducing the actual force that you experience. Right, back for everyone, we're now on our energy sources, again listed on our advanced information for the triples. If we talk about energy source, this is something we can use for heating, transportation or generating electricity. We categorise them as either renewable, will not run out, non-renewable, they will run out because they are being used faster than it's being made. So your non-renewables, nuclear and fossil fuels, coal, oil, natural gas. Renewables, the rest. So biofuels, the sun, tides, geothermal, hydroelectric, etc. Those are all renewable. Now, in terms of what we're actually going to do with these energy sources then, heating, tend to use fossil fuels, using a few more biofuels now, and in some countries they use geothermal particularly. Transportation tends to be our fossil fuels, think petrol and diesel. And generating electricity, this country we still have a heavy reliance on fossil fuels. But obviously we have nuclear power stations, you've got the kind of wind turbines, you've got solar sort of panels these days. All of those allow us to generate electricity there. One of the questions they do like to throw in here is looking to see why energy use has changed over time, and they quite often throw in random graphs on this one. So reading graphs, probably going to come up on this in some way, shape or form. Key reason though that our energy use has changed over time is down to the ever-increasing human population. So the more people there are, the increased demands there are for electricity, transportation, etc., and that all drives up the use of our energy sources. They can throw in this word finite, and finite just means that there is a limited supply. So that means we are going to run out of them eventually. Now, obviously we are quite reliant on fossil fuels, as we've said, and that is a problem. Firstly, we generate carbon dioxide, so we are generating a greenhouse gas when we burn them. If we generate large numbers of greenhouse gases, then that can lead to climate change, problems of climate change, the ice caps melt, sea levels rise, we get flooding, more extreme weather events, etc. And what we actually find is we need to consider how to try to combat this whole thing. But it's not just a simple case of we're not going to use any more fossil fuels, because we need to somehow meet those energy demands through alternative means. So we'll have to consider the cost, the new environmental impact, how long the source we're transferring over to would last, and then make a decision about what we can do. So it's not quite an overnight thing, contrary to what we all would hope for. Now, once we've generated this electricity in our power stations, we need to transport it to all the different regions around the country. And we do so through the national grid. So the national grid is this little series of power stations, cables, pylons and transformers that allow us to get the actual electricity from where we've made it to where we need it. So we are going to have step-up transformers. They increase the potential difference. We then have step-down transformers, decrease the potential difference. And obviously we then get to our homes on the far end there. It is worth remembering, for those of you doing the physics higher tier, that when wires heat up, we are transferring energy to the surroundings. Remember, if we're heating them, then we're actually transferring energy to the thermal store, and therefore eventually it will dissipate into the surroundings. We are wasting energy. Now, the amount of heating depends on the current and the resistance, and therefore by increasing the potential difference, what we're actually going to do is reduce the amount of energy that we lose through that heating effect. So that means we don't have to burn as many fossil fuels in the power stations, because we're not losing as much of the energy in transmission as we would do otherwise. For everyone then, we need to remember these two numbers: 230 volts, 50 hertz. That is mains electricity in the United Kingdom. 230 volts, 50 hertz. And it is alternating, so AC, okay? So it's an alternating 230 volt, 50 hertz. Remember that, they throw it in there quite often in those multiple choice. If we're talking about something like a battery, that would be direct. Now, one of the things that they can put in here is looking at the good old plug. So colours of wires, another easy question that might come up. In a typical UK plug, we've got 3 wires. You've got the brown wire, which is your live wire, the blue one is neutral, and the yellow and green stripy is your earth. We also have this thing here called the fuse, which is basically a safety device. Inside there is a thin piece of wire that when too much current flows through it, it melts the wire, breaks the circuit, and therefore shuts everything down. So what we can see here then is we've got a few safety features. Fuse is one, but we also have this earth wire. Now the earth wire is all to do with protecting you if that live wire comes loose. Because if the live wire comes loose and touches the metal case, you can become electrocuted. So what we need to do is have that earth wire that then connects to the case and the earth on your home, and basically it will allow the current to flow into the earth wire and safely away. It will not flow through you, because it takes the path of least resistance, and that is the earth wire. Another safety feature we could see is something called double insulated appliances, which is where the case is plastic and therefore it's an insulator. We will not have current flowing through it, so they don't need an earth wire. And now we come on to this last part of P8, which is for our GCSE physics folks. We are onto space. Now, first thing to remember is one of these questions they sometimes just throw in randomly in a range of contexts, is in terms of why scientific ideas change. It's because when we've got an idea that's been around for a long time, such as ideas about what the universe is, we are happy to accept that until observations no longer support it. So if we've got observations that can't be explained by the existing idea, what we need to do is come up with a new one. So this is how we come up with new scientific ideas. So, Big Bang Theory first of all. What we have in the Big Bang Theory is basically the theory of how everything began. So the universe starting as something incredibly dense and tiny, so something smaller than an atom that went this massive expansion about 13.7 billion years ago. So this massive expansion from this tiny little point is the Big Bang. Now, what we do know is that the space between the galaxies that we can see is expanding to this day. And we are not the centre of this entire universe. We are just one tiny little part of it. Obviously, coming up with an idea like this, we need some evidence to back it up, and there are two key bits of evidence for the Big Bang Theory. The first one is what we refer to as cosmic microwave background radiation, or CMBR. Now, quite simply, this is the fact that wherever we point a device to record microwave radiation anywhere in the sky, we pick it up. So microwave radiation is coming from all directions. And scientists actually worked out that this was the leftover radiation from the Big Bang itself. Live is most definitely blue. Now, what we actually find is that that high energy, high frequency radiation that we originated with at that point of the Big Bang has actually become stretched over time. And remember, we're talking 13 billion years here, so it's a long time. It's been stretched, and it's now sitting in that microwave region of our electromagnetic spectrum. So what we see there is we've just changed the actual sort of frequency of that particular energy, and therefore we're sitting in the microwave region. The second piece of evidence is what we refer to as red shift. So what we actually find then is, as far as red shift goes, we need to think about what happens to light as things either move away or move towards us. So this is something called the Doppler Effect. It's something you will have experienced if you've kind of stood on a street corner and something that has sirens has gone past you. It sounds different as it approaches than it does as it goes away. So what we see there is you get this change based on where you are in relation to it and whether it's coming towards you or moving away from you. It's the same idea with the light that comes from these distant galaxies. So Hubble actually did this. He measured the speed of galaxies based on the absorption spectrums of the light they emitted. And what he worked out was that when a light source is moving away from you, then the wavelength is going to actually increase and the frequency decreases. So when we increase the wavelength, we're moving it towards the red end of the spectrum because red light has a longer wavelength. And that means we are undergoing this process called red shift. We're shifting it into the red part of the spectrum. The faster away the source is moving, the greater the red shift is. Opposite is going to be true if it's moving towards us. So if that source is moving towards us, what we find is that the wavelength is going to decrease, and therefore it gets moved into the blue end of the spectrum. That's called blue shift. So red shift moving away, blue shift moving towards us. And what Hubble did was he used this red shift to work out, number one, that galaxies are moving away from us because they were demonstrating this red shift because they are going away from us and therefore moving to the red end of the spectrum, and that the more distant galaxies are actually moving away at a faster rate. So those galaxies in the far reaches of our universe are moving away from us faster than the ones that are closer to us. So that gives us the support for the Big Bang Theory. CMBR, redshift. There are two key bits of evidence there. We now need to move on to thinking about our little neck of the universe, our solar system. Now, hopefully, we know that our solar system consists of a single star, our sun. We then have the planets, which are going to be orbiting around our sun, various moons that orbit around planets. We then have things like dwarf planets and asteroids, and we've got comets. So asteroids are rocky things, whereas comets are ice and dust. So two different things there, but they both orbit around basically the sun in different ways. Now, in terms of the planets of our solar system, you should know the order of the planets, I would hope, working from the sun going out. And we start with our four inner planets: Mercury, Venus, Earth, and Mars. All of those are rocky planets. They all have an atmosphere of some type. That doesn't mean they are all the same. What we find is the type of atmosphere varies between them, the number of moons varies between them, but they are all rocky and they all have some form of atmosphere. We then come to the outer planets, Jupiter, Saturn, Uranus and Neptune. They are the giants. So Jupiter and Saturn, gas giants, Uranus and Neptune, the ice giants. And they're kind of key things they've got in common with each other, loads of moons and rings. The only other kind of thing we need to know where it is within our solar system is the asteroid belt. So the asteroid belt is found between Mars and Jupiter, and basically these are the lumps of rock left over from the formation of the solar system. And in there it's quite vast, it's not just a teeny little stretch of the world. It is in fact so big that it contains things like dwarf planets as well, like Ceres. That is a dwarf planet within the asteroid belt. This is triple stuff, yes. Now we need to come on to life cycle of stars. Now the key thing about the life cycle of stars is you must use the word gravity if we're talking about formation. If you don't use the word gravity somewhere in an answer about how stars form, then you've thrown away 1 mark guaranteed. So, in terms of how stars form, the start of their life cycle is the same in all cases. We start off with this huge cloud of gas, which is called a nebula. Now, all those individual particles within that gas cloud are going to be experiencing little pulls of gravity. So they get pulled together by gravity, and what we end up with is this large ball of gas at the centre of that nebula. The denser it gets, the more gas is pulled in because the pull of gravity gets stronger, and it gets hotter until we get to this point cooling a protostar. Now that protostar is going to continue to grow larger because gravity keeps pulling those bits of gas in, and it's eventually going to get to a point where nuclear fusion can start. So when nuclear fusion occurs, we are now at the point we refer to as the main sequence. And this main sequence star is the stable part of the life cycle. So this is where it just sits for potentially a very long time. That's where our sun currently is. When we now come on to the death part of our stars, we've got 2 options depending on how big the star is, which is all determined by the mass. We're going to start off with small stars like our sun first of all. So at the end of the actual star's life, what's going to happen is it's going to cool and expand in order to become this thing called a red giant. We then have these outer layers of the star breaking away, and they form this thing called the Planetary Nebula, which is basically these outer layers of star that are going to then potentially go on to form a new star in the future. And the very core, the very centre, we've got this white hot core left over, and that is the white dwarf. Over time that white dwarf will cool down until it just fades away in a very sad end of its existence. If we come to the larger stars then, these ones are obviously much greater mass. What happens is they still expand and cool, but because they've got a greater mass, they get into a much larger size to become a red supergiant. If it's big enough, we may even see it explode in that thing called a supernova, so a giant cosmic explosion. Now, if it's gone into that supernova phase, what we find is the core of the star gets crushed down by these huge gravitational forces to make this neutron star, which is incredibly dense. Now, that neutron star is also going to spin really quickly, and as it spins, it actually sends out these pulses of radio waves. And if ever you're really bored, you can find videos on YouTube of basically neutron stars that you can listen to, because you can record the radio waves, which radio waves we can turn into sound, and you can listen to the stars. If we've got one of these much larger stars, then that core is going to be crushed down beyond the neutron star into a black hole. So the black hole itself then is basically this incredibly strong pull of gravity within a tiny area. And when we're talking about an incredibly strong pull of gravity, we're talking about so strong that not even light can escape it, hence black hole. For those of you doing higher tier physics, we need to know about satellites and their orbits. So, first thing, satellites can either be natural, the moon, or artificial, all of the ones we've sent up into space. Think Elon Musk and all his satellites, they're artificial. Now, in terms of the artificial satellites, we have two orbits we use for them: geostationary and low polar. The geostationary orbit is the one that's going to take 24 hours for one orbit, which is the same time that Earth rotates once on its axis. So think about geostationary as a word. Geo, talking about Earth, stationary, not moving. So these satellites sit above the same point of the Earth's surface at all times, because they orbit at the same rate that the Earth rotates. They've got a much higher orbit, around 36,000 kilometres, and we use them for things like communication satellites, because we know that it will always be in that exact same position, so we can send a signal up and then relay it back down. Option 2, the low polar orbit, this one has a much shorter orbit time, around about 2 hours usually, and they're closer to the surface of the Earth. The key thing about their orbit, it goes over the poles. So what we actually find is that it goes all the way over the poles every 2 hours, and therefore we can use it to get up-to-date images of the surface of Earth. So think military satellites, weather satellites. This allows us to literally track hurricanes because we get up-to-date images of what's happening. Same idea with military movements. You can literally watch troops move using these low polar orbit satellites. Do remember that when we talk about orbits, if something is in a stable orbit, then that means that the object is moving at the right speed for the distance it is from the object it orbits. So think the planets in our solar system. They are all moving at a certain speed that is perfectly tuned to where they are with relation to each other and the sun. So what we find is the further away from the sun we go, the slower the planets move. That's because that pull of gravity from the sun is lower to those distant planets because they're so much further away. So we've got a much smaller force changing the planet's velocity. It moves slower. For those of you doing physics higher tier, we need to know about radiation and temperature. We've already touched on this earlier on by saying that obviously objects will emit electromagnetic radiation. A warm object will emit this infrared radiation. You are all currently emitting infrared radiation into your surroundings because you are all maintaining body temperature around 37 in theory. Now we can detect the amount of infrared radiation from a thermal imaging camera. Combined, you're done. You can actually go and just revise, have a break, go to sleep, whatever it may be that you want to do. This is just for the triple folks for the end. Now, the type of radiation that we emit depends on the temperature of the object. So what we tend to get on that thermal imaging camera, different colours based on the amount of radiation, remember. And we can apply this to stars because we can't send a temperature probe into all the different stars that we can see in the sky. However, we can work out the temperatures of those stars from here on Earth. So hotter objects will emit more radiation of higher frequency and shorter wavelength. So quite simply, by analysing the light that comes from different stars, we can then work out which ones have this higher frequency actual radiation being emitted. If they've got a significant amount of high frequency radiation emitted, they are hotter in temperature. If they don't have much of this high frequency radiation being emitted, they are a cooler star. So we can work out the temperatures of the stars purely by looking at what radiation they are emitting there. One question they do throw in occasionally is looking at basically what happens when they emit and absorb radiation in different amounts. So if we're emitting more radiation than we're absorbing, then we are going to see a temperature decrease. If we absorb more radiation than we emit, then we are going to see a temperature increase. And if we emit the exact same amount of radiation as we absorb, the temperature remains constant. So just think about which is greater, what direction is a greater amount of radiation moving in, and that will tell you whether it's cooling down or increasing in temperature. And that ties in to the whole idea of, obviously, climate change again, because we talk about the radiation from the sun reaching planet Earth, where it's going to be absorbed by the surface there. It then emits radiation because it's warmed, therefore it emits radiation. Ordinarily, a lot of that goes straight through our atmosphere back into space. However, if we increase the concentration of greenhouse gases in the atmosphere, a greater proportion of that radiation will actually be absorbed by those greenhouse gases and then radiated back to the surface, leading to that mean increase in the Earth's surface temperature and therefore climate change that we discussed earlier. The very final thing we need to do is the structure of the Earth and how we've worked it all out using seismic waves and good old earthquakes. So, physics higher tier folks only. We need to know that there are basically 4 internal divisions that make up our Earth, the planet. We've got the outermost layer, the crust, then the mantle, outer core, and then in the very centre, the inner core. There it is. So crust, mantle, outer core, inner core. This is what we know the structure of the Earth to be. It's not because we've literally stood on the surface here and drilled right the way to the centre. We've not sent anything down there in terms of probes. That's impossible because it's too deep and it's too hot. So no probes would actually be able to do that. Instead, we've got this information from earthquakes because an earthquake produces seismic waves, which we can detect on those devices called seismometers. Basically, think about a fancy machine like a pen on a little thing that moves as the Earth vibrates. Pretty much a basic seismometer. Now, the seismograms that they generate give us the time of arrival and the intensity of the 2 types of seismic wave. P waves, the primary waves, and the S waves, or secondary waves. So what we end up with is this kind of setup. Here is our earthquake, so this is where our earthquake originates up here. Across the surface of the Earth, we're going to have different seismometers picking up any seismic waves that they can. So if we've got a seismometer up here, then we're going to detect both P waves and S waves. Whereas, we actually have these things called shadow zones, which basically are areas where only one of those waves is going to be detected. And the reason that we get those shadow waves is down to the nature of S waves and P waves. So what we have then, P waves are longitudinal, so they're able to travel through both solids and liquids. S waves, transverse waves, they can only travel through solids, they can't travel through a liquid. So quite simply, in order to work out that the Earth's structure is like this and work out which bits are solid, which bits are liquid, if we just have a little look and see where are we not picking up those S waves, then we know that somewhere between the point that the earthquake exists and that seismometer is a liquid, because it's something that's blocking the S waves getting there. If the P waves are picked up, we can be absolutely certain that it must be a liquid there. So that was our original idea of actually working out the fact that the core must be liquid based on that basic principle, and then another scientist built on that work. And what they actually did was they analysed those P waves to work out that actually the very centre, the inner core there, is solid. So we have this liquid outer core and a solid inner core. And from further analysis of those seismic waves, we've actually worked out the sizes of all of those divisions. So we now know the sizes of the inner core and the outer core just from those seismic waves. And that is it. Don't forget tomorrow to take a calculator, because I would expect there to be calculations on this paper. Do remember obviously your ruler as well, because they've certainly put on about reflection, refraction, etc. on that pre-release, so ray diagrams are a possibility. Draw in pencil so you have more than one chance. Read your questions carefully, particularly breaking distance and thinking distances, and then just enjoy the fact that that's your last exam for most of you, I'm guessing, and enjoy the longest summer you will have in your lives. So at the end of that exam, hopefully you will go out, enjoy your summer and not worry about the results, because you've done all you can. There's no point stressing about it. Enjoy your summer. I hope you found this useful, and you never know, I might see some of you for A-levels next year.